So I will not apologize in the first 3 talks. No L functions and no zeta values will appear at all. But the properties of the L functions and their values, which are of interest, have their origin in algebraic and arithmetic properties of modular forms. And that's the topic I will talk about first. And also I will not apologize for any difference in attitude with Alexei. And also not if there are some non-empty intersections. So sometimes you will hear things twice or perhaps with different aspects. So the main title of my talks could be intrinsic algebraic and arithmetic properties of modular forms. In brackets you can add to be applied to properties of zeta functions. So, and intrinsic means, first of all, it's done without mentioning any kind of L functions. And of course, arithmetic means some integrality properties are involved. So, so this means, in particular, Fourier expansions and possibly congruences, and also Hecker operators. And maybe I put 2 brackets because this topic will probably not appear so much. Congruences among eigenvalues, and last talk, or maybe last 2 talks, so here the L functions and L values will definitely appear. Okay, so, but today, okay, and I should say, Alexei has already explained that there are different frameworks to consider modular forms. One can do it as function of the group. You can look at, instead of looking at automorphic forms themselves, you can look at representations, but you can also look at them defined on a symmetric space. Yeah. These are the 3 things, and I want mainly to look at modular forms defined on symmetric spaces. That is, if you want something like a classical point of view, that modular forms are functions on some space. And however, and this is the main topic of today for me, that if you consider modular forms from a classical point of view, in several variables, you still need some representation theory, even then. So even if you want to look at modular forms in a completely classical framework, you have to use some representation theory. And one reason I want to stress today is only in such a way you will see that we can give a definition of modular forms which does not contradict the French constitution concerning égalité. I hope this word appears in your constitution. No, actually the usual definition of modular forms does not cover the majority of modular forms at all. It just ignores them. And I want to show you how this comes up quite naturally, even if you don't want. So today, how does representation theory enter into well, I should say in several variables. Let me use an abstract setting here. So I write G, K, X, X0 here. And G at the end it will be the symplectic group or GLN, but it can be any topological group here. This is a compact subgroup. This is a topological space on which K acts transitively, so such that X is isomorphic to G mod K. Yeah, or maybe other way around. And X0 is a fixed point of K. I just do this. I could. Most of the things I do will be rather formal, so I could have as well taken any group, any subgroup, any set on which G acts transitively, or you could do it in a differentiable setting or whatever you want. So some aspects of it, what I'm going to talk about at the moment, are purely formal, and the smoothness of the situation will not really matter so much. But keep in mind GKX. And one thing more, maybe gamma a discrete subgroup. So only two cases will be cases to be so G maybe GLNR or SPNR. Now, SPNR has been defined by Alexei this morning. This is the isometry group of the standard alternating form. K is O and R, or maybe I write it already explicitly here. Yes. Set of A minus B, B, A. So symplectic group is 2n by 2n, and I request that the matrices have this form. This is n by n blocks, such that A, this way around, yes, IB is in U and C. So this is a group isomorphic to the standard unitary group. Okay, so U and C sits in SPNR in this way. So, and X, depending again on these two situations, is either something I call Pn. This is symmetric matrices with positive, it's a positive definite, or we have Hn. This is a set of all z equals x plus iy and Cn n such that y is positive definite. Symmetry. So this is Siegel's upper half space, and this is the space of positive definite symmetric matrices, and the action G and Y, G and GLN is G transpose YG, and here GZ goes to AZ plus B, CZ plus D, inverse ABCD is equal to, is in SP. This is Siegel's upper half space. Well, and gamma would typically be lesser than Z or SPNZ, but this is only for simplicity. And our main interest is this space of Siegel's upper half space, and what is the advantage of this symmetric space over this one? Well, you might think GLN is nicer than symplectic group, but this has a Hermitian structure. Here we can talk about holomorphic functions. Here it's more difficult to extract functions with nice properties. Here we will use just holomorphic functions. No? Okay, and what else? X0 will be 1n or I times 1n. Do I need anything else? No, that's it. Yes. So you just should keep this in mind, and I will come back to this after telling you what I want to say. So let's go back to this general setting here. So of course this was covered also in Alexei's very more abstract introduction. There are three ways the first one is, and this I will ignore here, I will erase it immediately. This is by harmonic analysis. So what do I do? One, there's a 1b. Yes. So take a so, and here you could put any properties you wish. Yeah, maybe you want continuous functions or differentiable functions, the infinity functions, or it is as you want. It doesn't matter at the moment. But on this space, you can produce new functions by substituting g by g times g1. Yeah. This is something people call right regular representation on this function space. So, so this is a G module by right representation. To say it again, such a function of G can be made into a new function by looking not at the argument G, but at the argument G times a fixed element of the group. Huh? And now you can ask to decompose this space so this is harmonic analysis, and it's in particular you can do it in a L2 setting, that you request these things to be square integrable, and you have a Hilbert space, and you can try to decompose this Hilbert space as a representation space of G. Now this is terrible. You will have continuous spectrum and discrete.
Representations, or decompose it into irreducible. No?
It is not so easy with irreducible. Cusp forms, yes, they will decompose into irreducible ones, but you have a continuous spectrum as well. This is a theory of Eisenstein series. Yeah? So you have a continuous and a and a discrete spectrum here. So, but let's forget about this. This is infinite dimensional representation theory. We will ignore this here. I just wrote it down for completeness. Yeah. So this infinite dimensional representation theory. This is some work of Langland's on this L2. Yeah, so the second thing is, in fact, this is my main point here. This is representations of K versus automorphy factors. This is a notion which has to be explained. This is today's topic, and the third topic will be, and this has appeared almost tacitly in Alexei's talk, when you want to define L functions, you will need a representation of the L group, so definition of L functions. This will not appear today but later. And these two things I have to emphasize, they have to do with finite dimensional representation. Whereas this one would be finite dimensional representations. Okay, and so the third topic will not appear today, I'm afraid. Okay. Now, remember, K is compact. So in principle, this is something simple. No? And let's ignore gamma moment, or put it just equal to trivial group. That is also possible. And we just look at f, g, v. This should be the set of all functions g to v, such that v gk is equal to rho of k inverse v of g, k in k, g in g. So these functions, the components, think of v to be c to the m. Yeah? Then the components of these functions are complex valued functions on G. So appear in f of G without gamma. Yeah? And naively, you could think about acting on this space here by K from the right and decompose this space under representations of K. Yeah? You can try to decompose this kind of space here by the action of K from the right. The advantage over this problem which I erased is that the group is now compact. Yeah? Still, I do not want to write down that it's a direct sum over the irreducible representations. Chi, did I write chi? No, rho. Rho I wrote. This I don't need. But let us look at this space here. And if you want, you can put in some invariance properties or not. So now, one has to be careful. When I write this space here, then differently, that's the reason why I ignored gamma now. Here, I modify G by multiplying from the right with a fixed element of the group. Yeah? Since now I have imposed some condition when multiplying things from the right by K, I can modify this G now from the left. Yeah? If instead of G I take H times G and consider the new function of G, then it still satisfies this. So I have on this space, again, I have an action of G. So now, these functions here, we understand what's happening if we multiply the argument by K. And remember, X, the space, was G mod K. No? So, what you attempted to try is to identify these functions here with functions on their space X, G mod K. Of course, you have to be careful. It's not like being just, if it were like this, just invariant under K, it is not a problem at all. Yeah?
Put the light on, please. It's nearby to you.
What?
Light on the black light.
Ah,
the switch on the wall.
It's a switch on the right.
No, I don't know what you are.
The light.
Ah, this. Ah, sorry, I could not. So, sorry. Yeah, but unfortunately, it's not like this. Yeah, otherwise it would be just functions on the quotient. Yeah, so. So, the question and this is the point where the automorphic factors come in. Because you cannot just simply go from the functions on G, transforming on the right by K. You cannot go directly to functions on X. No? Where am I? Here. Okay. By definition, this is a function of G cross X to automorphisms of V with a co-cycle relation. Now let me write the action of G2 on X in this way. So, okay. This is just a definition. And automorphic factor adopted to this representation rho here. So we observe that K goes to J of K x0 is actually a representation of K. Why? If G1 and G2 are K1 and K2, but you apply K2 to x0, and x0 is a fixed point of the action of K. Yeah? And here again you get G2 x0, so it's a representation of K. And you request that this representation is rho. It is a representation anyway by this definition, but we request that it is the representation rho. Now, in the simplest of all worlds, how would you get this automorphic factor? Suppose you could just extend your representation rho of K to G. So then you could just take J of G comma X to be this extension of rho. Yeah? But you will not in general be able just to extend this representation of the compact group to G. You may not enlarge V. Yeah? The representation space should remain the same. Yeah? So if you could extend it, everything would be fine, but that's usually not the case. Yeah? Okay. Is the representation rho. So, and now I want to transfer my functions on G to functions on X. Then, taking for granted the existence of such a J, for phi in F GV, now, this also appeared in Alexei's talk for GL2, but the other way around. He started from a function on the upper half space and produced a function on GL2. We do it other way around. So now we have to define it by f of x to be j of g x0 phi of g. This is definition of this f. G in G with G x0 being equal to x. Remember that the group G acts transitively on the space X. So this means we have in any way attached to a function on G with values on V, we have attached a new function on X, again with values in V. So is in, what did I call it? F of x, V functions. So this is so okay. This even gives a okay. Let me. And the question is now, how can we interpret the action of the group on phi now on T of phi? Yeah? We want to see how this works on the space of functions defined on X. So GV and for H in G. I forgot something. Oh. Definition independent of choice of G, because if you, well, which kind of freedom do you have? You can change G by an element K. Yeah. So then you have phi of gk, and this gives you rho inverse of k, and here if you use this property and this one, this will be compensated. Yeah. So it's independent of choice of G. So okay. 2, 3. So now for phi, so this is the action of g on these functions. And now we have to see what's happening with t of phi h of x. Now, phi h of g Now I express this in this phi now in terms of f. F was defined here. So then I get this factor with the inverse. So I get j of hg x0 inverse f of hgx0. Now using this cocycle relation here, I get j g0 j g x0 inverse j of h gx0 inverse f of hgx0. So this goes away. This is important. So, and now this is j of h x to the inverse f of h x. Huh? Okay. So now let's take this as a definition of an action of g on this space of functions. No? F. So so the rho indicates that this j, this automorphic factor, really depended on this representation of k. And this notion is a so-called slash operator. And this is okay. This is the action from the right, on these functions. Action of G on the right on fxv. And this is compatible. We have t of phi h of x is then t of phi rho h. Oh no, I don't need the x here. So this gives you a natural action on the space of functions on x. Yeah, and now gamma comes again into play, and we have fxv. Gamma is the set of all f on x with values in v, such that for all gamma in gamma we have f slash rho gamma is equal to f. No? So, okay. Yeah. So, and where does the French Constitution come in? I still did not say anything about the existence of such automorphic vector. Case x so this the representations of the unitary group, irreducible representation of the unitary group, they are in relation to the well, this is a maximal complex subgroup of GLNC. Yeah, and they come from rational representations of GLNC. So usable representation such that rho tilde is rho. The other way around, if you start from GLNC and restrict, this is something that goes under the name of unitary trig. Yeah? So that is now in Hn. This is a representation of GLNC. Yeah? This does what you want. Oh. Elementary. This J is So, and now concerning the égalité, there is no reason and no justification to prefer characters of the unitary group over higher dimensional representations. Yeah? So these automorphic factors and these spaces of functions with values in the representation space of GLN come up naturally. No? If you would take the rho to be one-dimensional, a character, then you would just get determinant of CZ plus D, and you would get power of that, and then you get something scalar valued. Yeah? But there is no reason why such automorphic factors coming from the characters of the unitary group should have more rights to exist. Yeah? Maybe you consider the higher dimensional representations to be more complicated, but you cannot blame those representations for that. Yeah? And so the space, and I should say,
How do you see that
and then,
determinant in the one-dimensional case?
pardon?
How do you see that it becomes the determinant in the or power of the determinant?
Well, if you well, what should be when you look at the one-dimensional representations of this unitary group, you just get determinant. Yeah. Of this A plus IB, yeah, what had been there to identify these things. Okay. And now I can properly define the space of modular forms I think one has to consider. Rational irreducible representation. So So this will be functions on this Siegel upper half space with values in V for all gamma f slash rho tilde gamma will be equal to f, and remember this means rho of Cz plus D to the inverse f of Gz. Yes, and we request this f to be holomorphic. So, and this is the space of degree n. Modular forms for rho tilde. Maybe the tilde I will ultimately forget. Okay. Now I have to tell you that already in 1958 in the Séminaire Carton, in the exposé by Godemont, these things were all clearly written. But when you look at books on modular forms, these vector-valued modular forms are completely ignored in most cases. Only the case where the row tilde is just the determinant is considered as a modular form of weight k. No? Of course, in degree 1, the ordinary modular forms, this does not matter. This is, representation will be just one-dimensional. No? This is U1, U1c. But here there is no reason to look at only to look at the scalar valued ones.
You see, because it was written in French, because the monk is in French, so people maybe did not read French.
Yeah, you can download the seminar carton. That is not a problem. Okay. So this is the space of functions I want to look at.
Sorry, but are you going to fix gamma to be SPN or?
For convenience now. It could be any congruent subgroup of gamma. Or one more word I should say about confusions. When you look up maybe in Google vector valued modular forms, you will get something else. Not this one. Maybe Zagier has to be blamed for this. In the context of Jacobi forms, people introduced vector valued modular forms where this vector valued comes from a representation of the group gamma. No? You know this Jacobi's modular forms and the theta expansion. Their representations of the group gamma come in. Of a finite, with co-finite kernel in general, but this is an abuse of language. But when you look up in Google these things, you will meet those vector valued modular forms. But the vector valued thing comes from a representation of the group gamma. But this is independent of gamma. This comes from the Lie group. Now, Godemont, he knew both. He even considered both cases, and he called them formes modulaires de poids ρ et à multiplicateur mu. Mu was the representation of gamma. He considered things where both appeared. Okay. So this will be the space of modular forms we are going to consider. Okay. Now, I will rather shortly. I have to explain some properties of these polynomial rational representations. This is what is written in the table of contents on the highest weights and so on. So. Did you call, Alexei, did you call the Borel group Bn, or what did you say?
B.
B, just B.
You see, maximum torus is sometimes called borus.
Ah, yes. So, now let just some exercise in linear algebra. Let the group of so this is a group. Group of upper triangular invertible matrices act naturally on C to the n. I hope you agree with this.
So, not understood before time. So, like for S&P, you have not only the automotive factors, you also have this multiplier systems then. So, the multipliers for.
Well, then the value of these things is in a space of homomorphisms from one representation space into the other. You can. I think the only place you can find this is really in Godemond's, I think it's Seminar Content 58 or something. You can find it in the web. I recommend this generally. Okay, but you agree with this linear algebra, yeah? So upper triangular matrices, there's one-dimensional invariant space generated by this. This you can see, you can give it as an exercise in first year linear algebra, but this is only the tip of the iceberg. This is still true if you let this group act by a representation, by irreducible representation on some vector space. So you have a row, irreducible representation interplaying here, not this simple way. You will still have a unique one-dimensional invariant subspace generated by 1, 0, 0. And this is a theorem by Lee, which I like very much. It is quite general. So G is some connected, solvable group. Rho G, maybe I call it B. It's irreducible, of course, continuous representation. Where am I? 3, 4, yeah. Irreducible continuous representation. Then the dimension of V is 1. See, if you go to some irreducible subspace here, it is a one-dimensional space. Yeah? But this statement here is the basis of this. You have to do some induction over the degree of solvability, going to quotient groups, but it's a very nice proof. What does it help us? Now, here. Let me state the following theorem. This time pi dl and c finite dimensional and rational representation irreducible. So, several statements, some of them trivial, others not so trivial. The first one is V has a vector, maybe non-trivial here, not zero-dimensional here, has a vector such that pi of n applied to V0 is V0. with a character of C star. C star. This is very clear. You just restrict this representation to the upper triangular matrices and apply this theorem of Lie. Yeah, possibly going to a irreducible representation of the Borel subgroup. Actually, you don't need to do that. So I even did not need irreducible here. If pi is irreducible, in particular, this means that the restriction of this representation to the upper triangular matrices remained irreducible. Yeah, because otherwise you would get several such things. Yeah. Called highest weight vector. So this character here of C star cross C star is not completely arbitrary. Then chi Now, up to now, this is not very exciting, but K1 to Kn do not appear arbitrarily, but it's like this, K1 equal to K2. So, and this is called the weight, this tuple. So, where? Here. This was C, now there is D. Of course, unique up to equivalence. Okay, there are several things hidden here. For B, I already mentioned that it implies in particular that the restriction of the representation remains irreducible. And here the statement really is the second part, that we have these inequalities here. And in D, two statements are hidden, that first of all, such a irreducible rational representation always exists with this weight, and it is unique. Yeah, so we can uniquely characterize the rational irreducible representations by this tuple of integers. Now, this is not the main point of our work here, but this we will use. And one remark which if you prefer natural numbers rather than integers, the Kn can be characterized as follows. The Kn such that determinant to the minus Kn tensor pi is so if these things are natural numbers, then we have polynomial representations. No? So the negativeness here just indicates that we have a negative power of determinant, which we can factorize away here. Okay, so I was wondering what I'm doing. Examples. Maybe we should have some examples. Some of these will appear later on again. So if pi is just identity gln C to gln C, well, what is the highest weight vector in V? Vector you can just take here, and the highest weight. Well, after all, it's just multiplied by d1, highest the weight is 1, 0, 0. So I hate these trivial examples. They are not very illuminating. I should generally say the existence of these representations is not so directly achievable. I know two methods. One is you go into the book of Hermann Weyl on classical groups. There it is shown that if you take the tensor representation, it takes a natural representation, just the one which I took here, take sufficiently many tensors of this, and then you decompose this into irreducible representation, and you will find this inside. Yeah, maybe this is a classical way, but there is another way using so-called bideterminants. By those you can do this more explicitly, perhaps, but this is a matter maybe of choice. I don't know any other method to show the existence of these things. Yeah, maybe the oldest one is in Hermann Weyl's book, but this thing with bideterminants may have been in the thesis of Sophus Lee already. So it's not so. People may. This is something for the historians. I have more examples. Yes. So, where have we been here? Yeah. Of course, that L So this is weight L, okay. And pi nu, this goes like this. So this is, yeah, I take V to be C polynomials in n variables homogeneous. Degree nu, and if you have a phi inside here, then so you somehow switch around these things here. Highest weight vector x1 to the nu, and the weight is nu 0, 0, 0. And the final example I have here, which I like very much, and it will appear later on again. Matrices of size n over r. So how does n by n matrix act on symmetric matrices of size n over r? I will explain this in a moment. I hope I do the transpose on the right side, but this may be possibly wrong, but it does not matter so much. Where so this consists the collection of all R by R subdeterminants of this matrix. Yeah? This gives the n, when as coordinates you take subsets of rows and columns. This gives you an n over R matrix, and the adjoint matrix of G entries are subdeterminants or determinants of submatrices of X of G of size R. Now
just R as the exterior product. Yeah, R exterior product.
Pardon?
R exterior product. Lambda R or not?
I think it's correct, like this n over R. Size determinants of submatrices. So, yeah. So pi is irreducible of highest weight of weight 2, 2, 2, 0, 0. And here you have r times you have 2, otherwise you have 0. And highest weight vector. Now vectors are matrices, symmetric matrices. This is 1. The matrix which has just the 1 on the left side here. Yes, so far about the examples. These will appear again when I talk about so-called theta operators, maybe in the third talk. Okay, this was kind of crash course in representation theory of GLN, and I have left some minutes to explain naively Heck operators. And we can go back. So let me say naive definition. I can do this in this generality because we will use it also again for several times. Gamma and gamma. Okay. So we have here some function on our space X, values in V, invariant under gamma. As before. We call that we can act here by the slash operator and rho. So now we take any delta in G. Then we can move it around by delta, but it will no longer be, in general, in this space because the invariance under gamma gets lost. Yeah? This delta can be any element in this topological group. But what it does is it's invariant under this conjugate group. Just abstract nonsense. Yeah? When you apply something here, element from here to this function here, this delta carries over. So now we have messed up this F. Now let's correct it, let's make it beautiful again. This is a wrong group. So, and now, since this is invariant under the wrong group, we make it invariant under the correct group by averaging. And what kind of averaging do? We take gamma intersected with delta inverse gamma delta. So this is again in f x d gamma. So where is the mistake here? There is no algebraic mistake, there is an analytic mistake because this sum may be possibly infinite. Yeah? So Yeah? Possibly it also works more generally, but algebraically it works under this condition. And I can slightly rephrase this. And then you will recognize that, well, maybe some of you know Hecke operators by double cosets. And you are maybe wondering why I wrote it in such a strange way. Well, this is written by double cosets, because this is the same as writing the sum f slash, now I have no new names, say delta, gamma, I take epsilon. And where is epsilon running now? It runs the double coset gamma, delta, gamma, modulo, gamma. Just algebraic reformulation. Yeah? The representatives must be of the form delta times some gamma. And you just look at this form. The representatives must be of the form delta times some element of gamma. And the elements here, they must just be like this. So, and this is the usual rephrasing things as by double cosets. So the conclusion is all double cosets gamma, delta, gamma with this finiteness condition yeah. So pretending that there are many such deltas with this property star, we get an abundance of endomorphisms of our vector space of modular forms without knowing the space of modular forms. Yeah? We have possibly infinitely many endomorphisms for one-dimensional space. Yeah? So, okay. Maybe this is a good opportunity to stop, and I will then start next time more abstractly to talk about these Hecke operators. Yeah? But I wanted to make clear in this setting that this is a very simple construction. Yeah? You first spoil your function, then it is invariant under the wrong group, and you correct this by the finite summation. Yeah? And this you can do in this general context. Yeah? But next time I will go specifically to these operators or to the double cosets in the case of GLN and in case of SPN. And then we have to talk more concretely about the explicit structure of these Hecke algebras.
Do you discuss attacking?
Yes, this is part of this. So thank you for your patience.
Okay. Question?
Thank you.
Yeah, by the way, I sent to you this, what you mentioned, Cartan seminar. Okay. And you could put it on the webpage, yeah? For those who interested.
Yeah.
But it is available.
Yeah, I downloaded it. I think it's from 50. Number 9 and 10 or something, yeah? And the expose by Godemont.
On my webpage it is.